Good afternoon. First of all, I'd like to thank the organizer for giving me this opportunity to speak here. And I feel so honored to be able to speak in a conference which is held in honor of Professor Yang, a person who has influenced many generations of overseas Chinese, from my primary school teacher to my university teacher. But here I want to talk a little bit about how the gauge concepts, the gauge theory has extended beyond high energy to many other fields. So we hear a lot of talk about the future of gauge theory. And indeed, I would like to take this opportunity to say that this is indeed the case. I'm from the engineering community, and now the gauge theory is also used by a lot of people in the engineering community. So the three major institutions in Singapore, the Nanyang Technology University, the National University, and the A-Star, and I work in these two places. So these are the people who work with me, and you can see they come from different fields, and many of them are actually from the engineering community. In fact, all of them are from the engineering community. Okay, so before I go into how the gauge theory is used here, I give a brief introduction of what I mean by applied physics here. So as we see, we have the universe, I mean the particle physics and stuff like that. And if the atoms are all put together like this, they define a band structure, and then you have the electrons basically filling up the bands, and then you have the condensed matter physics here. And then recently people talk about mesoscopic physics. So that part of the condensed matter physics where you actually need to restrict their dimensions. So now technology allows us to make two-dimensional system where it is confined in one dimension. And if you confine them in two dimensions, you have something like, the one-dimensional nanotube system. And then recently people are actually able to confine them in all dimensions, and therefore this becomes a zero dimension, something like a quantum dot kind of thing. And the next step, we need one more step to go to making this into a device. To make this into a device, you need to push the carriers to make the carrier flow across the device. And therefore, the simplest way is to apply voltage, electrical voltage that drives electron across this device here. So this is the applied physics is in this region here, where the condensed matter system has been reduced in dimensions, and external fields are applied to drive the carriers in this systems here. So very, very generally, I mean, in the condensed matter system, it depends on the band structure and the number of carriers we have here. So if you have a lot of free carriers, they fill up to very high, and then you have something that behave like metal, and if they don't go beyond that, beyond the gap, then you have something like a semiconductor. And then recently you also have the carbon, and there's a lot of development in things like graphene and carbon nanotube. And even recently, even in the insulator, people find topological effects here. So along this axis here, basically in the applied physics, we don't use a lot of particles. We only use mainly electron, and we are concerned about the charge of the electron. And recently, people are also concerned about the spin of the electron, and of course, the photon here. And this matrix here defines the different areas of applied physics that is recently catching a lot of attention. So to give an idea of what I mean by devices here, so there are many types of devices. So one example is the memory. So we know that in the computer we have memory, and memory stores information. So two crucial features of the memory is that one must be able to write the data in a memory. So after writing the data memory, we must have a mechanism to read back the data here. So here, the first row is about the different mechanism that can allow a person to store data in the device. And here, there's a series of mechanisms that allow people to read back the data. So I just briefly described the first one, which is the simple and common one, is that you have, say, a layer of ferromagnetic material, and the magnetization direction, as you see, there are two directions here. So the magnetization directions of up and down will represent 1 or 0, which is the information that's needed, in the computer. And how do you switch them? To switch this data, to switch the magnetization from up to down, so the simplest method is to use a magnetic field to do the job. And okay, so once we have done that, we need to know what information we have written in the system. And so how do you read them? So one of the very common method is called the magnetoresistance, that allows one to tell whether the data is up or down, because they give a different resistance strength. And resistance can be translated to voltage, and voltage can be measured very easily with a voltmeter, for example. So how does the gauge physics come in here? Now, there are many types of gauge that can be used here. So I focused on 2 types here. One is related to the spin-orbit coupling. Spin-orbit coupling in the vacuum is not that strong, but in device, there are certain ways, in recent times, certain ways of making the spin-orbit coupling to be very strong in device. And therefore, and people look in terms of the gauge. So now, before I go into this, the phenomena of, so I will briefly relate gauge to velocity and forces, because in device, you talk about electron motion, and you need to see how, if one knows how the gauge is related to the electron motion, and then you see how it is related to, for example, the current and the voltage that you can measure. So now the relation of gauge to the velocity and the forces actually lead to a series of very useful phenomena here. So here I'll just focus on 2 in my talk here. On the far left is what we call the Spinorbit Talk, and the other one here is called the Spinhole effect. Now the reason I focus on these 2 is these 2 effects have a particular relevance to device, a memory. For example, a Spinorbit Talk can be used to switch the magnetization. And once you have done that, you have done a data writing. And Spinhole is actually the inverse of this. Spinhole allows one to detect the resistance change, and therefore one is able to read back the data that you have written. So it's remarkable, it's marvelous that we are able to relate the writing and reading mechanism to some very nice and fundamental theory. So here is just very quickly, for example, to say that if one has a Hamiltonian on the left-hand side, we do it in a very classical manner. If from the Hamiltonian, one can easily derive the velocity, and also a magnetic field which has some similar structure to the Young-Mills field here. So now we just go back to very classical physics here. So is the Lorentz force. So if we imagine that you have in the Lorentz force, you have the magnetic field here, and then you have a velocity in one direction, you would have a force. One can conjecture that you will have a force in the transverse direction, as shown by this diagram here. So naively, or based on just pure classical intuition, you put together something like this, we put together something like this, and then we expect there is going to be some kind of forces because of the velocity and the spin orbit gauge. So this is just pure imagination here. Now let's do a simple quantum mechanics to see if this is true. So once do a simple Heisenberg and found that you can have something that is like a force here, which is given by this one. If you compare the 2, they look similar with the exception that on the left-hand side, you do not have that A here. But they look similar enough so that they give the idea that in the presence of spin-orbit coupling, one is able to extract some kind or to detect some kind of forces that would eventually or hopefully be useful in the applied physics. So here is just a summary of what I just described. We do a classical approach on the left-hand side here, the classical way. And then you do the Heisenberg way. When you combine the 2, you see a simple force equation here. And then we can also define the current. Instead of the current being just a charge current, we can define a current to be a spin current, for example, in this way. And then when you combine the two, you can see a relation in the last equation here, a force equation that actually relates the Spinhole current to a force. And the type of gauge that we use here is a simple type of gauge that arises from the Spinorbit coupling. Now to go one step further, in a Hamiltonian like this one, we also can have a gauge by performing a rotation, a unitary rotation of the system, and one is able to see in the last row here, number 4, we are able to see that one is in the time space, the other is in the momentum space, that we also have an additional gauge here, a gauge as a result of rotation. And of course, you have a series of approximation and adiabatic and stuff like that, but eventually you would have a combination of the two gauges here. And now, combining the two and going back to the simple intuitive approach, then one is again able to see that or derive a force equation that is related to the electron or the spin current in the transverse direction. So all this gives us the confidence that the gauge effect can be useful in the applied physics. So now going back to this, I will go right into the Spinorbit Talk, something that we can use to do data writing, and the Spinhole, something that we can use to do data reading. So before going into the Spinorbit Talk, of course, I have to explain a little bit about how a memory works in the engineering, in the applied community. Now, this represents 1 bit here on the right-hand side here. On the right-hand side here, this is 1 bit. But 1 bit is not enough. For memory, we have billions of bits here, right? So now, if you want to make a memory, you have to integrate these billions of these using a structure which is like this below here. So here you go in one direction, and then the other direction you go into the board here. And it is therefore an array of bits with billions of them here. Now, but the physics, the crucial physics are here. You know, in that part, the small part of the device up there with the up and down magnetization. So which is described by something on the left-hand side here. So you will have one layer, which we call the free layer, which stores information. And then you have another layer called the pin layer, the fixed layer, that allows one to inject spin current to switch the information. And that is the job of writing, data writing here. So this is the background. Now, how the Spinorbit Talk comes in here. So here recently, people found that in a device like this, you don't need 2 layers actually. You don't need the pin layer to generate the spin current. So we make things more efficient and simple by by using just 1 layer. How about this? How about if I have a layer with very strong Spinorbit coupling, and I use this layer to generate spin current. And at the same time, this layer also stores information in the form of magnetization, which means I can do 2 things together, which is first, to convert a charge current into a spin current, first step, and second step, to use the spin current to switch the magnetization. Therefore, people are making use of the Spinorbit coupling to switch the magnetization, and that's what we mean by Spinorbit Talk here. So it is given by, one can see that this effect indeed happens. The left-hand side is the ordinary Hamiltonian with Spinorbit coupling and with magnetization. So all you need is a material system, is a material system that has 2 things. One is the magnetization, and the other is the Spinorbit coupling. And as recently as 4 years ago, this material was found. And therefore, this becomes possible. It's just not an imagination. So if you look at this equation here, it is possible that for this system, you can do a simple rewriting of the Hamiltonian, that the Spinorbit coupling is coupled to the momentum here. And the magnetization remains here. Now we go to the right-hand side, you perform a rotation here, so you get 2 additional terms here, these 2 additional gauge here. So this gauge is related to what we call the Spinorbit Talk. The gauge here it comes from the spin-orbit coupling, and it is also coupled to the magnetization through the unitary matrix U here. And if one do it carefully, one can actually derive a torque from the second term here. And the third term here is related to the Spinhole effect. So it's remarkable that in the same Hamiltonian, you actually get one effect for data writing. I would say, to relate in engineering words, this is for data writing, and then this one is for data reading. So the summary of what has been done is that all this summary can be summarized in one equation called, the famous Landau-Lifshitz-Gilbert equation, which was first written in 1935. So, so the first line, that equation about the dynamic of the magnetization has been used for many years in micromagnetic calculation, and is only as recently as 20 years ago, in 1996, people added a term called the spin torque term, and 8 years later, another type of spin torque term is found, and so this LLG equation gets modified along the way. And in 2007, we actually derived the spin-orbit torque, and we feel that this spin-orbit torque will be useful for writing data. So we first derived this torque in 2007. And subsequently, in 2008, the same formula was also derived by another group in the United States, and also by another group in Japan. Now, what is important is experimental confirmation, and which comes in the year 2010 by a group in France, and then many other groups from the US and Japan, who continues to see that this spin-orbit torque that we derived earlier can actually be used. They demonstrated it in experiment that it actually can result in the switching of the magnetization, which means the spin-orbit torque can be used to do data writing. But of course, I also want to highlight one thing here. This spin-orbit torque needs not necessarily be derived with the gauge theory. We probably are the only group to do it using the gauge theory. And for example, in many other groups, there are many other methods, of course, to derive this. Oh. So here is to show just how hot this topic has become, the spin-orbit spin torque. There are many experimental papers that keep coming up, in the Nature type of journals, and they keep detecting new and strong types of spin-orbit torque here. Kyunsu is my collaborator from the NUS. He did a lot of experiment in this, and he published a lot of experimental paper about how the spin-orbit torque can be used to do the switching that I've been talking about. And I also want to take this opportunity to highlight one thing. As recently as last year, there's another spin-orbit torque. As I said earlier, that in 2007, we derived the first spin-orbit torque. In 2014, another spin-orbit torque was discovered and also derived, experimentally discovered and also theoretically derived. And according to the author of this paper, Bayashi, this spin-orbit torque is actually related to what he called the geometric Berry space. So I haven't studied carefully, but if you think about it, the geometric Berry space is again another relation to the gauge theory. So it is very remarkable that the two spin-orbit torques that are now being used in experiments all have their origins in the gauge theory. Okay, so now, so much about spin-orbit torque. I go to the second part, which is the spinhole. Spinhole is what I said earlier, the effect that if we use spin-orbit torque to do the writing, we use the spinhole to do the reading. So just a summary of what has been done recently. There are, again, many methods to do spinhole. So the first one, done by Japanese, Murakami, is related to the geometric and the gauge physics. And then also, there are people who use the Kubo formalism to do it. And then there's the number 3. There are people who use the Spinorbit gauge, and there are also many other semi-classical treatments. There are many ways to do this. But just very quickly, spinhole was actually first found by Diakonov the Soviet era scientist in the year 1971. But here, we want to say that the few mechanisms that have been used to derive Spinhole may not be complete. I mean, we want to say that. And we think that we should do it more carefully. And when you do it more carefully, you find that some of these effects have to be considered together. In fact, all of them have to be considered together, and you may get additional effects. So this is I just briefly show the result here. If we do it carefully, we see that the spin-Hall velocity actually consists of the kinetic term, the spin orbit or the Yang-Mills term, and also the gauge term, which was derived by Murakami and Fujita. So, and therefore, you examine it carefully. You have the kinetic term, you have the Yang-Mills term, and you have the Murakami-Fujita terms. So these are the velocity. They are all related to the spin-Hall. Now we want to say, we borrow a simple example, a two-dimensional example, and we want to say that in order to get the proper spin-Hall conductivity, you have to add them all up together. So here we use a simple two-dimensional system, and we did a calculation carefully. It is very important to look at the positive and the negative sign. It can be quite confusing. So when we add all the three terms together, the kinetic, the Yang-Mills, and the Murakami, and we found that the spin-Hall originally proposed or originally set for this system to be minus E over 8 pi, but when you add them all up together, the conductivity should be positive E over 8 pi. So the result should be the negative, the opposite in sign to the previous result. So we did the same for another system here, which is related to the whole system. And again, we get a negative sign here. So the summary is that using conventional spin-Hall conductivity that was done about 10 years ago, now using the method that we think is a more careful method, we get a reverse of the sign for the spin-Hall effect. That's all about my presentation here. So in summary, I just want to say that the gauge theory can be related to a Spinorbit Talk, a mechanism that can be used to write data, and it at the same time is related to the Spinhole effect, a mechanism that can be used to read back data. Thank you.